So I'm going to show you the motivation of the talk. My motivation, because that's not the... So you have here the drill string. At the bottom, you see the drill, the bit, and this thing is made to perforate the earth. So we're going to see some animation of this. So the bit, so you have the earth here, and the bit's going to start to rotate and start to perforate the earth. I don't know why this normally is not like this. Can you pass the second one? Okay. Can we have the second one? So what I'm going to show you, the second one is this. You see, you have the thing, it rotates, then stops, then rotates again, stops. This thing I call stick slip. The third one, so I'm going to show the same thing from another point of view. You see, rotates, stops, sometimes rotates backward, and this is the stick slip. So I'm going to talk about this. Okay, thank you. So the outline of the presentation, I am going to show you some motivation. That's the thing I showed you. And I'm going to discuss the dynamic of the stick slip oscillator. Then I am going to construct a probabilistic model of the base speed. You are going to see what I mean by this. Then a construct of a statistical model of the system response. Then I am going to discuss the total stick duration and total stick duration. And finally, I am going to show a parametric analysis of the statistical model. Since these things are technical, I think it's best if I show you what I mean and then explain a little bit better this outline here. Well, I am going to talk about a model. And my first slide is one of my heroes, Jorge Luis Borges, who talks about what a model is. Essentially what he says here, that if you make a model that's too truthful, too perfect, it's worthless. The idea of a model is exactly to capture the essential point and make the simplest thing you can. And I hope we did this. This is the same thing said in another way one time by Alfred Korzybski, and this one I am going to leave for you to discover who said that. If the guy is Belgian, cannot answer the question. Madrid. Okay, so that's the thing I showed you. I start showing you this. You see there is a motor here that drives the drill string. There is at the bottom the drill bit that perforates the earth. And the important thing is this interaction between the bit and the earth. And what we want is to perforate. And since this is a very expensive process, we want to do this as fast as possible, using the minimal time. So if this thing here sticks, it's not good. So what's the thing? when you start the motor, this thing starts to rotate, and the bits start to perforate the earth. And because there is friction here, high friction, this thing is a rock. Sometimes the rock holds the bit. And when the rock holds the bit, this thing does not stop, continue to rotate. So this thing stops, and this starts to rotate. So the drill bit, the drill string, works as a spring. You start to, you see, to have potential energy, elastic potential and resistance. Then suddenly this thing frees itself, and the thing continues. So what's the model we're going to study? What's the representation we want? We want this. We want to represent we want to represent the drill string, the elastic element, just for a spring. So this thing represents the drill string. The mass of the system, the whole thing, I concentrate just in one particle. There is no dimension. The motor, the model is made by a belt, so the driving belt. We model this, the effect of this motor here. And the important thing, the interaction between the bit and the rock is done by a friction force. So I'm going to make a model of friction and modulate this. That's the second slide. So this thing here is modeled by this, a very simple system. Okay, now the motivation is exactly to study the stick slip in the drilling process. But stick slip does not appear only in drilling process. For example, if you have, if you peel a tape from Scotch tape, you put in a table and then you peel it. You have the same process of stick slip. You have this in physics in several situations. So stick slip is in some sense one of the basic dynamics of nature. One can encounter this all over. So it's interesting to model this thing. So I talked to you about this, and the other thing I want to add is this. I'm going to model friction as the simplest Coulomb model. That means I'm going to use only one coefficient, not two. It's the simplest model one can use, and I am to analyze the stick slip through a stochastic process. And what I want to see is when the sticks appear. That's the first question. Then I want to know how long they last. Then fix an observation period. How is the average process? Because if I know the average process, I can in some sense hope that I can control the drilling process. And then I want to characterize the uncertainty of the process, and I am going to explain what I mean by this when the thing appears. What I mean by this will be to show how the mean process, how the average process is affected by dispersion. So that's my equation, that's my model. And I want to model this as a mechanical system, very simple one. So I have a mass, I have a spring, and I have a force that's made by the belt. So this thing here, I'm going to model as there is a slip velocity. V is the velocity of the belt. X dot is the velocity of the mass. I say that the friction coefficient is mu, and the normal force is mg. So the model is this. That's the friction force, mg, friction coefficient, and the sign of the velocity difference. And if v and x dot are different, that's the model. When v is equal to x dot, this term is 0. And if v is equal to x dot, there is no acceleration. The acceleration is 0. So during the stick part, the dynamics is governed by this equation. And f cannot be anything. F is bounded between the maximum and the minimum. That's exactly mg times the friction coefficient. So f maximum is this. And what I want to do to study the process is study these two equations. So that's my framework. In order to give you an idea how the dynamic is, I'm going to show the phase plane of this problem. So I am going to change a little bit. I'm going to use in the phase plane y, that's the velocity, and I'm going, instead of use the position, I'm going to use a z that has the same dimension as x dot. So this thing is the natural friction of the mechanical system. So if you solve for the phase plane, you get these two equations. If y is bigger than v, you get this. If y is less than v, you get that one. So this thing gives you this. So that's the phase plane. So if the velocity is positive, here is the place where you have a stick. So if you put the body, let's say, with some initial condition here, it comes, it sticks, it gets here, and then there's no more stick. You get a periodic solution. Here's the same thing with the velocity negative. You come to this point, and then the thing sticks, and finally you get a periodic solution. So if you have stick, you have only one. Either you do not have a stick, if you have one, you have only one. So that's the thing. So if the velocity is fixed, there is only one stick. And I know in my process that's not true, so I don't want this. So I want to use a discontinuous speed. First, I'm going to show you what's the situation if I have a deterministic process. Let's say I fix the speed, but I can change the speed, let's say, with a certain frequency that I call 2 omega b. B is for belt, so that's the frequency of change. So this thing here, I change with frequency 2 omega b. So if the ratio between the change of between the frequency of the belt and the natural frequency, if this thing is small, there is no stick. When I start to increase this ratio here, I can get stick. For example, in this situation, I get stick, this red one, but the thing is not so interesting. So I don't want to discuss this. I want to discuss the stochastic model that is the one that we can really see what's happening in the drilling process. So what I'm going to discuss with you is this. I have here a probabilistic model for the belt, how I'm going to change the velocity of the belt. So this thing will be a stochastic process, the base velocity. And I solve the dynamic problem of the mass, and I get a system response. So from the system response, I can sampling, and I get a statistical model. And what I'm going to discuss with you is these two things here. So I just said I am going to construct a probabilistic model of the base velocity. I'm going to generate sample of the base velocity. I'm going to process the sample. That means I am going to integrate the dynamic equation. And finally, I'm going to construct the statistical model and make some statistics. Okay. Construction of the probabilistic model of the base velocity. I say that the base velocity is described, the number of the discontinuity of the base velocity is described by a Poisson process. So I have this Poisson process here. Lambda in some sense, is the rate of change of the base velocity from 1 from minus 1. So if this thing is big, I change a lot. If this thing is small, very small changes. TA is the period of observation. So I start fixing a period of observation, is TA. And from this probability distribution, I discover the number of change to make a sample, and then through a uniform process, I choose from this interval, I choose any numbers. So n, I got n here, so I choose n points. These points are not ordered, so I order them. And these points here will be the points where the velocity is going to change. So this is the process. With this model, I can sample. So I make a sample, and this thing is the driving force for the process. So I integrate the equation. When I integrate the equation, I get something like this. For example, this point here is the beginning of a stick, and this point here is the end of a stick. For example, here I got a stick. Here it ends, then slips, then I get another beginning of another stick, and so on. In order to integrate this, depending of lambda, it takes a lot of time. Can take from a few seconds to 3 hours. If lambda is very big, some of the realization we made take 3 hours. Well, so let's discuss a little bit the stick duration. So one of the things I want to see, I want to discover, how is the stick and how is the slip and when I get them and how long do they last. So during the stick, I have this equation here. So one sees that if there is no change in the velocity of the belt, the maximum duration of the stick is this one. That corresponds to 1 point that when the sticks start, the spring is completely compressed, and when it ends, it's completely extended. So there is a big difference between stick and slip. Slip can last indefinitely, can last forever, but sticks have a maximum duration. So that's the maximum one. So one has to keep in mind this difference. So that's what I want to get. I just put here a picture to show you the sort of random variable I want to deal with. So I am going to study my process with this random variable that I'm going to tell you what they mean. For example, this thing here is the start, the instant that the first stick starts. Here starts the second stick, here starts the third stick, and so on. Here is the start of the first slip. That's the same thing as the end of the first stick. Here is the duration of the first stick, duration of the first slip, and so on. And what I want is to get this picture. As you see here, I put everything uniform. I said, since I don't know them, everything's uniform. So the random variable I have is the number of sticks, number of slips, instants where the sticks starts, instant where the slip starts, and the durations. I want this. Not, it can differ by one, but yes, if I know one, I know the other. As a matter of fact, there is much more. For example, if I have T1 and D1, I know L1. So I am not saying this. But you are right. There is a lot of relation between them. So everything I said, I wrote here. I have some discrete random variables, these two, number of sticks and slip, and I have some continuous random variable, they are here. So that's the thing I'm going to do. So I'm going to show you some results. I fixed some parameter values They are here. So the friction coefficient is 0.51. The time of observation is 10 seconds. That means I am going to integrate the equation during 10 seconds. Lambda, I am going to use, in this first part of the presentation, 5. So 5 is my first choice, and I'm going to show you this. And for those who care about the numerics, I'm going to use Hunziker fourth and fifth order, and with variant time steps. And I need this because if lambda, not now, but if lambda is too high, I have to use this. And my maximum step size is 10 to the minus 4th. So what one has here is if I choose lambda equal 5 and TA equal 10, so that's the histogram of the number of sticks. So I can have a realization and get this number of sticks and so on. Here's the mean. The mean is 50. So if I compute this, I discovered that for this situation, the mean of the number of sticks is 16.71, and the variance is this one. So it's the number of sticks, number of slips, I get this. Look that I am using 18,000 samples. I need this in order to have good histograms. In the second part of the presentation, I'm going to show you not the histograms, just the statistics. So I'm going to diminish the number of samples. I am going to use just 2,000. But if I use 2,000, I cannot show you histograms. They don't converge with this number. So here is the first 6 instances where the sticks begins. For example, here is the probability distribution of the first stick, the second, the third, the fourth, the fifth, the sixth. You see, this thing is being displaced to this part, of course, because, that's the stick. Here is the duration. You have here the first one, the second one, the third one. Remember that the support of the duration is limited. I have a maximum support. So this thing, the maximum thing is the number I show you. Here is the first 6 instants of slips. So here's the distribution of slips. And here is the duration of the slips. Amazingly, you see, I get bimodal distribution. I don't know why. I'm going to show you some. It's very hard to see the numbers from the histogram, so I'm going to show you some statistics. For example, here I have the beginning of sticks. So I get here the numbers. Of course, they have to increase. I get 1 to 6. The dispersion, they also increase. Here's the duration. It's almost constant. And the almost constant. Same thing for the slips. Same thing for the duration. These two do not vary. So if we make a graph putting the instants of sticks, the first, the second, the third, the fourth, and so on, you see that's the thing. The same thing for the slips. It's clear that T1 and T2 are not independent. What we did this is just to show making a histogram of T1, T2, the joint probability, and we discovered that that's what one found. And this is what one would found if they were independent. They are not. On the other hand, D1 and D2 looks like that they are independent. You see this thing appears the same. And in this case, the mean response of the stochastic, of the stick-slip oscillator, I have the average number of sticks. I have the average duration of the sticks, average duration of the sticks, average number of the sticks, the same thing for the slip. So I can compute the total time, and I see that in this situation, 1/3 of the time is stick. So if I am drilling, 1/3 of the time, the drill stops, and 2/3 of the time is, in fact, drilling. So that's the conclusion, and now I can somehow make a graph, and you see that the sticks is smaller than slip and so on. So that's the first part. What I'm going to do now is to show you the effect of the friction coefficient. I'm sorry. I have a problem here. Can you help me? I'm going to show you the influence of lambda is the rate of change of the belt and the friction coefficient. So in order to do this, to show you the parametric study, what we did is this. We choose 40 values of lambda, 8 values of friction coefficient, so 320, and we're going to do 2,000 integrations for each of these parameters. So I am going to do some 640,000 integrations. This thing is a lot. So just to give you an idea of the work, we did Monte Carlo, and we had 320 points just to study the parameters. And in average, this thing means nothing. Let's say we have 2 minutes. We use 2 minutes here because we know that this thing is true. 2 minutes, but as I said, if lambda is very small, the time of integration is some seconds. If lambda is very big, the time integration could be 3 hours. So if I want to do this, it's going to take me 2.5 years. I cannot wait this long, so we did this. We parallelized the problem, and it took us something like 2 months to do the calculations. And I'm going to show you what the results are. So we start with a friction coefficient of 5. And I'm going to show you 2 situations just to allow you to understand the problem. So first, I'm going to use a value of lambda. That means that the belt changes velocity very little. So there is almost no change. And I choose another value that the change is very rapid. It's 10 times a second. So let's see what happened. For example, if the belt does not change velocity, all the slips, all the sticks occur when the sticks ends when the spring is in the maximum, so it's in the very end. So in this thing here, see? The sticks always end in the maximum value. So if I have 10, it's completely different. Look at this. Here, everything's at the end, and here, everything's in the beginning. Because the sticks stops when the velocity of the belt changes. The sticks stops when the velocity of the belt changes. And what's happened is this. You see, I'm going to show you when I vary the parameters, you see this thing here starts to be displaced to the other side. Everything here is in the same unity. You see, this thing displaces from here to here. And what I'm showing you here is how the average duration varies when I vary the lambda. Então, the duration is diminishing as I increase lambda. And this thing here is the 95% envelope. So why does the stick duration decrease as lambda grows? It's interesting because when lambda grows, I have more sticks, but the duration decreases. What I want to know is if these two things compensates. So in order to understand this, I divide the sticks in two parts. One part, I look at the sticks that ends when the spring is completely, it's at the very end. So ends because of the spring. And the other thing, it ends because the velocity of the belt changes. So if I look at the two, I see they behave completely different, you see? And please take note that the scale is not the same. You see here is a big number, but you see, you have different scale. This thing do not compensate this. So here, one sees that when lambda is small, I have one point where the number of the stick duration is highest, and then it diminishes. On the other hand, this thing always increases. If I add the two, I get this. So as lambda grows, the mean of the stick duration decreases, and the mean of the total number of sticks increases. How these two things compensate each other is this. If you look at the two, you see that, that's the thing. One always finds a maximum point here, more or less in this region. So up to a point, they compensate, and then you see the time of sticks decreases. And here you have a graph that shows you, in function of the friction coefficient, the time, the average of the stick duration. You see the stick duration as function of lambda for different. If I look at these points here, the maximum, I can plot them, and I see how they vary. Okay, I'm going to summarize. I have a summary here, but why are you doing this? We're doing this to understand a little bit better how stick slips behave and try to use this knowledge to apply in a drilling process. Our next step will be to make a continuous model. We are in the process of doing this. Instead of doing the simple model, do the more complex model. And we are also doing a paper that studied the influence of the friction model. And what's our objective with this? Is this. I can get from a drilling process the picture of the stick slip. So I know in a drilling process how long what's the duration of the sticks. What I'd like to do is to make a sort of inverse problem and identify the friction process that gives me a certain type of sticks. So that's what I have to show you. Thank you very much.